Okay, so we are going to solve this example. It's the example 3.8 from Griffith's book, third edition. And this is a problem for a system that lives in a two-dimensional Hilbert space. Okay? So in a two-dimensional Hilbert space, we can write any possible state if I have a basis, for example, made of these two vectors, the vector 1, 0 and the vector 0, 1. And you see that these two vectors, with these two vectors, I can write any state. Now, these two vectors, they span the two-dimensional Hilbert space. These two vectors, they are normalized. Yeah, you can check that. If you compute this inner product, it is 1. And they are orthogonal. Yeah, so I have this orthonormal basis with which we can write any state that lives in this two-dimensional Hilbert space, and any state which will be a linear combination of these basis vectors. And of course, these states themselves have to be normalized. So if they have to be normalized, you can check that this implies that absolute value square of A plus absolute value square of B has to be 1. Okay, so this is the basis, and we are going to say that the Hamiltonian that describes this system is also lives in this two-dimensional Hilbert space, so it's a 2x2 matrix. Okay, and the diagonal elements are D, the off-diagonal elements are J. Your book writes this Hamiltonian with H in the diagonal and G in the off-diagonal. I didn't like this notation because we also have H bar, Planck's constant. I thought this would be confusing, so that's why I'm using this other notation. And now comes the problem. We are going to assume that our system is initially in the following state. So the initial state is that state 1 that we talked about, 1, 0. And what we want to find now is what is going to be the state later in time. Okay, well, what are we going to do here? The same thing that we used to do since the beginning of chapter 2. What did we do in chapter 2? Well, we would have a certain initial state, and then we would want to find the state later in time. So the recipe that we used here will be the same recipe to be used there. And what was this recipe? Let's remind ourselves. Well, first step, we had to solve time-independent Schrödinger's equation. We had to solve this equation to obtain all of the eigenvalues and eigenfunctions of this problem. And in many cases there, we had infinite possibilities. Well, it's the same story on the case of our two-dimensional Hilbert space. We'll have to solve the time-independent Schrödinger's equation. That's it. Now, it's a little easier now in our case because instead of infinite solutions as we had before, here we have just two possibilities. We will have an energy E1 and associated with it an eigenfunction S1, and an energy E2 and associated with it the eigenfunction S2. Nothing else. Okay, that's it. We're going to try to find that. Then step 2 in our story. Well, given the initial state, we would write it as a linear combination of our solutions of Schrödinger's equation. Same story here. We are going to write that initial state as a linear combination of our solutions. There are just two. So instead of that infinite sum as we had before, it's going to be C1 of S1 and C2 of S2. Very good. And what was the last step in this story? Well, the last step was, now that we have the state written at the linear combination, we find the state later in time by attaching to each of these cyans the equivalent, the corresponding energy. Okay, so that's the same thing here. Our final evolved state is just going to be C1 S1 with the energy of that state, and C2 S2 with the energy of that state. Okay, so the procedure is exactly the same. Well, but let's come back here. How would we find those CNs? So let's open some space here to discuss this detail. Huh? So those coefficients, those CNs, we would obtain by solving this integral involving psi n, the corresponding psi n for that Cn, with the initial state. Well, it's the same story here. So give some space. How are we going to find our C1 and our C2? Well, the C1 will be the inner product between S1 and our initial state, and C2, the inner product between S2 and our initial state, right? Because remember, how can we write that integral that we have to obtain the Cn? Well, it was in our new notation, just this. So that's what you see here, the inner product between the initial state and the eigenfunctions. Okay, all right, so this is the recipe. Okay, so let me make it all visible here. Given the initial state, so let's remind ourselves, write this down somewhere. Given the initial state, first we are going to solve Schrödinger's equation to get the eigenvalues and the corresponding eigenfunctions. After that, we are going to write our initial state as a linear combination of those solutions. How do we get to these coefficients? By solving this inner product of our initial state with each one of those solutions. After I have that, we just have to attach to it the energy, the exponential with the time. Okay, so this is the procedure. We are now going to continue. So I'm going to erase all this. This is just a review of things that you already knew. And let's go step by step now. Okay, so first step is here. Solving Schrödinger's equation. How do we do that? So now I make a parenthesis to tell you a little bit about the theory about linear algebra in case you don't know that, okay? In case you haven't seen that. But how we are going to solve this equation? Well, there is a method that is going to be easy, as you're going to see, but I just want to make a parenthesis to tell you a little bit where that method comes from, okay? So I'm going to rewrite this equation, transferring the right side to the left. So now this E here is just a number, no, it's an energy. And H here is a Hamiltonian, is a matrix. So look how I'm going to write. Once I pass that energy to the left, I put an identity matrix so that here I'm talking about matrices, okay? And this is equal to 0. Okay, let me call this whole matrix here some matrix M. If the matrix M has an inverse, and the way that we write inverse is like this, okay? So if it has an inverse, and I multiply this whole equation by this inverse, what I'm going to get is the following. The property of an inverse function is that I multiply a matrix by its inverse matrix, I get the identity. So this means that if this matrix M has an inverse, that means I killed my problem. S is equal to 0. So to be able to find the eigenfunctions, to find the eigenvalues, we cannot have, this matrix M cannot have an inverse, okay? Okay, now, how do we find the inverse of a matrix? The first step when we are trying to find the inverse of a matrix is to find the determinant of the original matrix and put it in this denominator with some additional terms here, the matrix of cofactors, okay? But the first important step is for the matrix to have an inverse, the determinant cannot be 0. Well, we do not want our matrix to have an inverse. So that means we do not want our matrix to have an inverse. That means that the determinant of this matrix has to be 0 for us to be able to find the eigenvalues and the eigenfunctions. The determinant of this matrix now is the determinant of Hamiltonian minus energy multiplied by the identity. The determinant of this matrix has to be 0. And this is the equation that we have to solve to find the eigenvalues. This equation is known as, some people call it the Secular equation or the characteristic equation. Okay, so this is a parenthesis, okay, just the theory behind. But now comes the method is that what we have to do to find the eigenvalues is to solve this equation here. Okay, and how are we going to solve that? Well, let's just write what that is. So the Hamiltonian has D in the diagonal, J in the off diagonal. And we also subtracting the energy. Né? So the energy here is multiplied by this identity. Né? So this matrix that we are writing here is this. Okay, so when I subtract my Hamiltonian by this matrix, I have here minus E minus E. And determinant, the notation for determinant is this, equal to 0. That's what we need to solve to find our eigenvalues. Okay, another parenthesis here. How do we find the determinant of a matrix that is 2 by 2? So the determinant of a matrix that is 2 by 2 is very simple. If you haven't seen this before, you multiply the diagonal and then multiply the off diagonal, but you put a minus sign here. Okay, so this is the equation that we are after. But there'll be other problems where you deal with matrices. They are 3 by 3. So let me remind you, or if you haven't seen this before, teach you how we find the determinant for a 3 by 3 matrix. Let me get some space here. So if I have this matrix and we want to find its determinant. Well, you may already have your method, but something that can be helpful, some students do that, is to copy this column again here, and then we go diagonal. Okay, so we have A, E, and I. Another diagonal, we have B, F, and G. Another diagonal, we have C, D, and H. And then we go with the off diagonals with the minus sign. Minus BDI minus AFH. And finally, minus CEG. We want this determinant to be 0. We want this to be 0. Okay, so you will see this kind of equation showing up in other problems that you will have to solve. But for now, things are very simple. We have this 2 by 2 matrix, so the determinant is very simple. Is the diagonal, so D minus E squared minus the off diagonal J squared. Okay, so that's the equation that we have to solve to find the eigenvalues. So the solution, I do the square root of that, I get plus minus J, so that the energy is either D minus J or D plus J. So I have these two. I'm going to put an index 1 and 2. We got our energies. So let's come back to that first step here. We found our energy. So the energy is D minus J is 1. The other one is D plus J. All right. We are done with this first step of finding the eigenvalues. Now we need to find the eigenfunctions or eigenstates associated with each one of these solutions. So first one, we want to find S1. How do we do that? Well, whatever this S1 is, it follows this equation. So I'm just going to write that equation. Now, that equation is Hamiltonian S1. The energy associated with S1 is D minus J, S1. All right. What is the Hamiltonian? I'm going to put it here. What is the vector S1? I do not know it yet, but all I know is that it has two elements. Whatever these elements are, I'm going to try to find. I'm calling it AB. If you want, you can call it XY, whatever they are, I'm going to try to find it using this equation. Okay, all right. So let me copy this equation below so we have more space. So this is what we are trying to solve. Well, what are there are two equations here. Then if I go first line with this column, we have GA plus JB equals to this first element. So equals to D minus J multiplied by A. Second line, we have JA plus GB, and second element is equal to D minus JB. Okay, this is my set of equations, two equations. There are things that we can cancel. Look, here we have dA, and here we also have dA. Here we have dB, and here we also have dB. So you see that this equation becomes very simple. It is JB equals to minus JA, and the one below, JA equal to minus JB. So J can also cancel, huh? So you see that what we find is whatever this vector is, what we know is that B is equal to minus A. Okay? Well, we reached this point. Very good. what is next? We still have to find A. And when there is only one unknown in the story, we go to our last resort, which is normalization. This has to be one. So let's write. So this one is the cat. Let's write the bra, this part here. And the bra is the line with the complex conjugate. So that's what it is. And the cat, A and minus A. If we do this inner product, we get twice absolute value square of A equals to 1. So we find that A is 1 over square root of 2. Okay? So our eigenfunction S1 is 1 over square root of 2, 1 minus 1. Okay, so we found one of the eigenfunctions. I'm going to come all the way up and put it here. 1 over square root of 2, 1 and minus 1. So now we have to go with the same procedure to find the other eigenfunction, the eigenfunction S2. But the procedure is exactly the same. Hamiltonian acting on S2 will give us the energy E2, S2. So it's exactly the same. The only thing that changes is the value of that energy, which is D plus J. That's where things change. So everywhere here, we just put this plus. Okay, so you see that the only thing that changes for S2 is that B is equal to A, so it's A here. Normalization is still true. So it's the same procedure. We get, again, 1 over square root of 2. So for the S2, we also have 1 over square root of 2, but 1, 1. Okay, so I'll come back and say, we are done. We found the eigenvalues, E1 and E2, and we found the eigenfunctions, corresponding eigenfunctions, S1 and S2. Okay, great. So now we go to our second step. Let's get some space here. Our second step now is to write our initial state as a function of S1 and S2. Well, here you are, how we are going to find these coefficients. So let's go one by one to obtain C, put it, to obtain C1, we have to do the inner product. Okay, so C1, S1 is up here. No, S1 is here. I'm going to, this is the cat. I'm going to put in the bra, so the line, there is 1 over square root of 2, 1 and minus 1. And our initial state, remember, is this vector here, 1, 0. So we have here 1, 0. So what is C1? 1 over square root of 2. And what is C2? Very similar. What changes is that here we have the state 1, 1, the bra for the state S2, with the initial state 1, 0, again, 1 over square root of 2. Okay, so we are done. Both coefficients are 1 over square root of 2. Okay, so we can come up here and we can say we found our initial state in terms of these eigenfunctions. This initial state is 1 over square root of 2 for S1, 1 over square root of 2 for S2. And now we can just attach to it the time. But before I continue, I want to show to you another possibility, okay? That in this problem is so simple, 2 by 2, that you don't need to go for these inner products. I think it's very good, it's very fast, but there is another way, which is to go straight. So instead of going like this, to find C1 and C2, you could have gone straight to this equation. And you say, oh, I have to find C1 and C2. What do I know? I know that my initial state is this vector 1, 0. I have to find C1. I don't know yet what it is, but I know what S1 is. S1 is this 1 and minus 1. And, well, I have to find C2. And I know what S2 is. 1 and 1. Okay, so straight from this equation, you would be able to find your coefficients C1 and C2. You see, because here we have two equations. No? The one equation at the top tells us that C1 over square root of 2 plus C2 over square root of 2 has to be 1. And the second line is minus C1 over square root of 2 plus C2 over square root of 2 have to be 0. So if you want, you can go straight here, and you would again find out C1 has to be 1 over square root of 2, and C2 has to be 1 over square root of 2 to satisfy this equation. Okay? Or you do as we did, which was to compute the inner product, whatever you prefer. Okay? Anyway, so we did with the inner product, we found that our state is, our initial state is 1 over square root of 2. For that eigenfunction S1, 1 over square root of 2 for the eigenfunction S2. So finally, we have our evolved state. 1 over square root of 2, S1 with the energy, the exponential of the energy E1 T over H bar, and S2 with the energy E2. All right, that's the solution, okay? But we are going to move a little bit more with it and put it in a very nice form. You will see it now. Well, what do we have here? Let's write what this state is. So this state is 1 over square root of 2, 1 and minus 1. Let's also write this state, 1 over square root of 2, vector 1 plus 1. Let's also put our energy. So this E1 is G minus J, and this E2 is D plus J. So what do we get now? What we have is 1 over square root of 2 with 1 over square root of 2, 1/2. 1 and minus 1. And here we have exponential of minus I D T over H bar and plus I J T over H bar. And the other one, again, 1/2, 1 and 1, minus I D T over H bar and minus I J T over H bar. Why I split the exponential like this? Because you can see that this is common to both. So I'm going to write our vector. Let's erase those things that are. Let's write our vector S. Both terms have this I D T over H bar in common. And now I'm going to put everything inside the vector. So the top line has I, the exponential of I J T over H bar plus minus ijt over h bar, all that divided by 2. Stare a little bit about this. See if this is familiar to you. Now, the second line, we have that minus sign. So I have minus exponential plus ijt over h bar. The next one is plus. And that divided by 2. Okay, so you stared a little bit at that and you say, oh, I recognize this top term here. This is a cosine, isn't it? Cosine of jt over h bar. And how about the bottom, the second element? There is a minus sign, and minus is where the sign appears, no? But the minus sign is in the wrong position. Look what I'm going to do. I'm going to put this minus in front of everything. So then I have to put also a minus here. Okay. So this is the form of the sign, but what is missing in this story is the I. I need an I here, so I'm going to add this I here and put it back here. So you see that this top term that we have is minus I sine jt over h bar. Okay, so we put our function, our evolved state in a very nice form. It has this exponential in front, and here we have cosine of jt over h bar and minus I sine of jt over h bar. Okay, that's the solution in a very nice form. There are things that we can do. That's the end of this exercise, okay? But I want us to discuss a little bit more the solutions. The solution, okay? What do I want to say? Look, this is the solution. I can also, where did this come from? From here, no? So let's just copy this again. And this is a state that is changing in time. Okay? So if I ask you, what is, if I measure energy, what is the probability that I get the energy E1? Well, we know this since chapter 2, that the probability to get, if I measure energy, to get energy E1 is the C1 square, so is the C1 absolute value square, which is half. Very good. And what is the probability to get energy E2? Same procedure. The probability to get energy E2 is absolute value square of C2, which is half. Okay. You already knew that, but I want to add one more thing to this story. You know that when we measure, we collapse the wave function. When we measure, and let's say, if we measure and we got energy E1, we are no longer in that state as T. After that, the system becomes collapsed. The system collapses to this state. Okay, so another way to talk about this probability to measure energy E1 is to say the probability to measure energy E1 is the probability that my state will collapse to the state S1. So the probability to get this state at the end The probability to get this state at the end is how much of it lives in this ST, how much of it contributes to this ST. So the inner product, but the inner product absolute value square. Okay, so the probability that if I measure my system and get this state S1 is given by this expression. And you can check. This is the same thing as C1 square. Let's check. So this inner product that I'm computing, absolute value square of that is what? Well, let me write my ST here. It has two terms. So this is 1 over square root of 2 S1 with the first element there. Okay, and then we have 1 over square root of 2. Now, with this second part, so S1 with S2, exponential minus the whole thing. All that absolute value squared. Okay, so this is the probability that if I measure my system, I will find my system in that state S1. Now, have a closer look at what we wrote here. We said that these eigenfunctions are normalized and they are orthogonal, which means this is gone. Well, so this inner product, absolute value square of this inner product, is only this part. Well, absolute value square of exponential with I, we already know is 1. So you see that what we get here is this C1 squared, S1, inner product S1 with S1 is 1. This we saw is 1. So you see, that's the C1 squared that we talked about before. Okay. Why did I do all this? Now, making your life much more difficult. If you already knew, you just had to look at C1 squared. Well, why this is interesting? Let me cut all this now. And this is interesting because energy is not the only thing that we can measure. We can measure other properties of the system. In this system here, I could have asked, for example, my system is in this state, but what is the probability that I find this system in this state 1 that we wrote in the beginning? Well, we never talked much about this state 1 and 2. We just played with it, but it could be physically indicating a real system. As you will see later when we talk about chapter 4, it could be indicating the two possible states of a spin, for example, a spin half. We could say, if you have already heard of spins, this can make sense. We could say that this state 1 corresponds to a spin pointing up, corresponds to a spin half pointing up in the z direction, and this state 2 corresponds to my spin pointing down in the z direction. Okay, so I have my system evolving in this state, and we could ask, what is the probability that if I measure this system, I find it in that state 1? I find it, the spin pointing up. How would I find this probability? I would look at, as we said, the inner product between that evolved state and that state up, which we are calling state 1, absolute value square. This will give us the probability to find the particle, the system, in that state 1, in that vector 1, 0. Okay? We could do this kind of measure. So it's not a measurement of energy, it's a measure of the spin, for example, pointing up. And this is the way to go. Okay, so we have to pick our state and do this inner product with the vector 1. So it's this vector 1, 0. And now it's convenient to have it written in this form, isn't it? We have I dt over h bar. Then we have that cosine of jt over h bar. We have the minus I sine of jt over h bar. So this is our probability. If we do this absolute value square, we can compute that. Again, absolute value square of this guy is just 1. It's going to disappear. If I do this product of this line with this column, what survives? I'm going to keep that whole thing there, but you already know that this term is going to disappear. No? And the product of these vectors just gives us the cosine. So, as we said, this part, absolute value square, is just 1. We got cosine square jt over h bar. You see that the probability to find our system in this state is changing in time. At time 0, it was our initial state. So at time 0, so let's write here. At time 0, the probability to find our system in that state 1 is 1, 100% there. It starts in that state. But if we go at a later time, for example, at time, what should we write? Time pi over 4, h bar and j. What would it be? Well, then the probability now is going to be cosine square of pi over 4, isn't it? H bar, j cancel. Cosine of pi over 4 is 1 over square root of 2, square, half. Okay, so at this time, we have 50% chance of finding our state, finding our system in this state 1. Let me pick another time. Time pi over 2, h bar j. What is the probability to find our system in that state? Well, cosine square of pi over 2 is 0. So you see, the probability changes in time. Okay, there are 2 more additional points that I want to discuss with you with respect to this problem. This is about probabilities, but let's now talk about expectation values. So, we have our system in this state. I'll keep it written in that vector form. And suppose we want to compute the expectation value. How do we compute the expectation value for any quantity? Well, the expectation value will be the sandwich. So ST, let's talk, for example, expectation value of Hamiltonian. Well, let's write it. If I want to find the expectation value for the Hamiltonian, which is the average value for energy, what I do? The sandwich. So the bra Hamiltonian acting on the cat. Okay, that's what we have to solve. The problem here is find the expectation value at any time, but we could say specifically find the expectation value at time 0, for example. Well, you can do it in general form like this, or you go straight to this. Okay? So let's find this case. How would we proceed? What is the initial state? The initial state is 1, 0. So let's put things together. The bra is 1, 0. The Hamiltonian is diagonal J diagonal, acting on 1, 0. So that's what we have to solve to find what is the energy. If you go through this whole procedure, well, let's do it together. This part first. This line with the column will give us just D. This line with the column will give us J. So this gives us D. Okay, very good. There is an interesting thing that I'll let you check. If you compute the expectation value for the Hamiltonian, the average value for the energy, at any time, you can check that, you will get D. Because the energy of this system does not change. Okay? The energy does not change unless we inject energy or extract energy, but we are not doing that in this problem. Okay, so the energy, the expectation value is the energy of the initial state. It does not change. Other observables can change in time. Okay, so other observables can change in time. I let you check that this remains true for any point in time. And that's the end of these additionals for this problem 3.8.